Can everyone hear me okay? We're good? Yeah. Awesome. Okay, so we're going to start this talk with an experiment. This may actually be the first sing-along that's ever occurred at GOTO. I'm not certain. It's definitely during the main conference the first sing-along. I can't speak for the parties or anything like that. What I'm going to do, I'm going to play a note on the keyboard, and I want everyone to hum or sing what note they're hearing, okay? Cool? Are we on board? All right. All right, thank you. More on that later. Who am I? So I'm a consultant. I write software for a living and work with a number of great individuals that also write software for a living for some great clients, many of which are in the room. Hello, clients. Thank you. I'm also the founder of a consulting company, which means I mostly check emails and scribble on whiteboards most of the time now. And I'm a speaker. Occasionally I speak. And I'm a co-author of a book that no one should read because it's like super, super dated. So this slide was supposed to be a picture of the Spantree team, but I totally forgot to take the group photo today because we had everyone in town with the exception of one of our team members in Belize. But there are some Spantreers in the room, so just raise your hand or stand up or do something weird. Okay, that's Spantree. That's most of Spantree. That's definitely a quorum of Spantree. Who else am I? I am a musician. I'm a composer, or at least I used to be. I'm a Spotify addict and just an addict of music in general. And I'm a recovering DJ. Sorry. This is a talk, though, about music theory. That's Mozart. He knew a lot about music theory, or at least what they knew about music theory at the time. But there was another historical figure, Pythagoras. For those that went to school in the States and lived in a certain era, is anyone familiar with this cartoon? Okay, because we're going to watch this cartoon now. You're going to relive my childhood experience just today. This will be great. Hopefully the video feed works. I haven't tested this part yet.
Let's go to ancient Greece, to the time of Pythagoras, the master egghead of them all.
Pythagoras?
The father of mathematics and music.
Mathematics and music?
Ah, you'll find mathematics in the darndest places. Watch. First, we'll need a string. Stretch it good and tight, plunk it. Now divide in half. Plunk again. You see? It's the same tone, one octave higher. Now divide the next section. And the next. Pythagoras discovered the octave had a ratio of 2 to 1. With simple fractions, he got this. And from this harmony in numbers developed the musical scale of today.
All right. And then it goes into like a whole other thing. But anyway, by the way, Disney Corporation, that qualifies as fair use. Please don't delete this video from YouTube after the fact. That was under a minute. It was under a minute. So let me talk about the impact that this this video and this specific cartoon had on my life. I sort of fell in love with Pythagoras. So this was actually my AOL screen name. It's Pythagoras spelled backwards. I tried to actually revive a desktop computer that had AOL Instant Messenger installed so I could take a screenshot. Don't try to do that. Don't try to do that the weekend before your talk, especially. Bad idea. I also, as a musician, released 3 albums under the name Pythagoras. This is an album called Pathology, and I also did 3 other albums called The Pythagorean Theorem 1, 2, and 3. So I was really into Pythagoras, and I was really into like all his ratio stuff. So more on that later also. Remember when I said I was a recovering DJ? So let's talk about college. College was a weird time where people sort of experiment and they try to find themselves, and they're somewhat lonely and they're trying to make friends and that sort of thing. And so I had some musical background, but I started out. I had a brief career as a classical composer in high school. I actually wrote some music for my high school orchestra. It sounded kind of That was me circa 1997. And then I had a slightly longer career as a MIDI musician. We would actually write songs. We all had like the same sound cards, and we would upload them to the internet in like bulletin board forum type things, and then we would like finish each other's songs. So this is an example of one of the songs that I worked on. I just wanted to get to that cool drum part. But then college happened, and this wasn't really, no one was really resonating with that, and people were really into this DJ thing, because parties. So I became someone that looked like that, hopefully not as far gone as they were, and hopefully not that guy in the back either. But I definitely did this a lot, and so we'll get into that in a second. But one of the things I did is, as a classical composer and as a MIDI musician and as someone that was really in love with Pythagoras, when I was working on DJ sets, I would apply music theory to those DJ sets. And a lot of the DJs that get paid like $20 million a year to go fly around the world and play Dubai and stuff, they also apply music theory to their DJ sets. And so this was actually like one of my more popular mashups. Has anyone heard of the term mashup? How about like mashup in the context of Web 2.0? Like where you take like two APIs from two different things together. That came from this notion of like taking two songs and putting them together. So this was one that I worked on sometime in the aughts. I can't remember exactly when. I think the date stamp's on there. But it's called Beyonce Rockin' Beats. And you can hear why maybe if you recognize the song.
Can you keep up? Baby boy, you lose my breath. Bring the noise, you lose my breath. Hit me hard, you lose my... Can you keep up?
Anyway, does anyone recognize those songs? All right, what the hell was that? What was that? I don't understand. Michael Scott doesn't understand either. So that was Beyonce, Baby Boy, and Chemical Brothers, Block, Rockin' Beats. And how do those two songs work together? Like what made them gel in a way that like most random songs wouldn't? Well, how did it work? Harmonics. And we're going to learn about harmonics today. We're going to learn a little bit about discrete optimization, but we're mostly going to learn about harmonics. Most of my talk is on harmonics. So remember Pythagoras, he came up with these ratios. And these ratios represent the frequencies, so like how quickly a wave travels, or how, like the period between the waves. And the ratio between those waves end up producing things that have sort of like pleasing sounds to the ear. And we're going to go into why it's pleasing a little bit as well. So these two particular songs are what are known as perfect fifths from each other. So this is from a website where they do some like key detection. And so you can see Beyonce's Baby Boy is in D flat major, and Chemical Brothers' Block, Rockin' Beats is in B flat minor. So they're perfect fifths from each other, meaning they're 5 notes apart on each other's scale. But since one is major and the other is minor, they're compatible. They basically share the same notes on the keyboard, they just have a different root note. And we'll go into a little bit more about that as well. Just as a poll of the room, who plays an instrument in here? Okay, who knows what major and minor are? Okay, for the rest of you, we're going to cover it briefly, or someone else is. I'm going to delegate that to someone on YouTube. But this is a really big principle in terms of like figuring out how to make songs progress. So this is a picture of the circle of fifths. As I said before, B flat is the perfect fifth of D flat. We'll cover more on that as well. Why does it matter? Why does it matter? Because the brain likes to do math, but not too much of it. So this is Adam Neely. Is anyone familiar with Adam Neely? All right, I got the serious musician in the room back there, the music theorist. So Adam Neely is probably like one of the more popular YouTubers, and he puts out a video series where he basically explains a bunch of music theory. And I tried to do a similar explanation in rehearsal, and it didn't go very well. So I'm just going to delegate to him to explain a few musical principles, and specifically how the brain processes sounds when sounds are tonal.
When the sound of the clips hits your inner ear, a structure called the basilar membrane will vibrate in sympathy with the total number of clips hitting it per second. Tiny hair cells in the inner ear will convert that acoustic information into electrical impulses that the brain can then interpret, just the same way that a microphone will pick up sound waves to be either amplified or recorded. What happens next, I think, is pretty incredible and also not that well understood. Our ears can do math really quickly.
I'm afraid we need to use math.
Let's take these two sine waves. One vibrates at 520 times per second and the other vibrates at 650 times per second. Your ear automatically calculates the ratio between the two of them as 5 to 4. This is the interval of a major third. Because 5 against 4 is a simple ratio with simple integers, our ear accepts it as a pleasing sound. Our ears automatically do what our conscious brains might have to labor over, quickly calculate ratios between two separate pitches. And boy, can they do it quickly. Thousands of notes per second can be processed by the brain with the right sort of math behind it.
All right. That blew my freaking mind the first time I saw it. Because I knew about the ratios, but I didn't really think about the fact that, like, the simpler the ratio, the more pleasing it is to the brain because the less work it has to do. But, like, you want some sort of variety to keep it interesting. It's like all other forms of sort of like artistic consumption. But what does it have to do with Beyonce? What does it? Does anyone have a guess as to what that has to do with Beyonce? All right, good, because it was a rhetorical question anyway.
Well, maybe the answer lies in the harmonic series. The harmonic series, also known as the overtone series, is based upon simple multiples of a fundamental. So if your fundamental is 100 hertz, the second harmonic will be 200 hertz. The third harmonic will be 300 hertz. Just take whatever the frequency of a note is, multiply it by a number, and then you get that number harmonic. So easy, even a musician can do it. We hear all of the different harmonics as different pitches and intervals in relationship back to the root. Our brains process the differences between harmonics as musical intervals. The ratios between two of them create a harmonic interval. For example, the distance between the fifth harmonic and the fourth harmonic creates a 5 to 4 ratio, or the ratio of a major third that we heard earlier. Major thirds are in our system of Western harmony, but other intervals aren't, like the distance between the seventh harmonic and the fourth harmonic.
Sorry about that. Was that last part was pretty displeasing to your ear, though, right? So it turns out, I'm just going to foreshadow a later part of the presentation. It turns out that people are making playlists with these intervals and not knowing it, and it's sounding awful. Especially if has anyone used Shuffle? Shuffle does that, right? Shuffle will do that because it doesn't understand music theory. So what we're going to be talking about today is building a better mousetrap, a shuffle sort effectively that understands musical composition and how we might be able to apply that. So let's go back to Beyonce and Chemical Brothers. So we just learned what a perfect fifth was. So there's a ratio between two frequencies, the fundamental. So now I'm going to go over to the keyboard and I'm going to attempt. All right, we can all see the keyboard. That's great. I'm so excited. I was very nervous about this. All right, so we've got a B or a D flat. Sounds like that. Right. Okay. And then we've also got a B flat. Okay. So if you hear these together, that did I get that right? Hold on. Yeah, D flat and a B flat. Okay. So the scale, if you watch the keys, nudge that a little bit over that way. So the scale, starting at D flat, if we're playing a D flat minor, sounds like this. Okay? Now, the notes from that scale happen to also be the scale of B flat major. What did D flat minor sound like? Did it sound happy or sad? Sad or a little weird? It makes you feel a little nervous, like something wrong is about to happen. And that's because the intervals of a minor scale are a little, they're less pleasing to our ear. They're a little bit more complex, and some composers would say interesting. But just to avoid any controversy, I'm going to say complex. So now let's play the B flat major scale. So same notes. I'm not very good at keyboards. Okay. So if I got those scales correctly, which I don't think I did, they would have the same notes. Because they have the same notes, if your ear gets used to listening to a song that has those notes, and then you go to another song that also has those notes, you're going to think like, I'm still in the same musical sort of like groove that I was before. Now, if I played something that was very dissonant, and I can't on demand, I practice, I can't do it. But if I played something that was what was called dissonant, where we had like some intervals that didn't really make sense, that would be jarring. That would kind of like screw you up and make you think like, well, this doesn't, like these two songs don't go together. I can't really, unless you're a musician and you can like just recognize keys and scales on demand, you may not know why, but you'll definitely like have it naturally in your brain that it sounds weird. So relative minor, just as a refresher, of D flat major is B flat. So they share the same keys, and you can sort of see those here. And we already saw it on the keyboard because I forgot the order of my slides. But while we're over here, remember that experiment we did at the beginning where we sang? We're going to do that one more time, right? So I didn't actually, I'm going to do that one more time with the keyboard thing here. Pay attention to these lights for a second. You don't have to sing unless you really feel it. You can if you want. So what I'm doing, this simulates a pipe organ. And back in the day, before we had these fancy like Nord synthesizers, in order to make sounds sound rich, what you would do is you would add harmonics. You would add intervals beyond the bass note that's played in order to make the sound full. And some of those intervals are actually intervals that aren't octaves of the same note. And so what I was doing with the red lights is I was removing certain elements so you could actually hear different tones. So when we were singing a note that we thought we heard, that was because we were hearing the fundamental frequency, but even hidden in that frequency, there's a number of other frequencies, and that also has an impact on the way that we perceive sound. There's actually only one sound that can't be produced in the natural world that has a perfect like flat set of harmonics that are only octaves. So actually that's too low for the speaker. So that's what's called a sine wave, and those are what you hear when you get like hearing tests and that sort of thing because there's no other stuff going on. But most music is not just sine wave music. That would be kind of weird. That would be actually really boring, or like, I don't know, it would be like new agey type music. Sorry, Yanni. I was really into Yanni when I was like 7. It was like one of like the 20 like CDs that my parents owned, and so I don't want to knock new age, but yeah, they use sine waves a lot. So that's a pipe organ, and so you can see there all of these different pipes have different lengths, and so that's what makes the sound full. The same thing applies for guitar, the same thing applies for flute. They all have what's called different timbres, and that timbre represents all the different subharmonics that are there. Are we still here on harmonics? Are we digging harmonics? Did we learn something about harmonics? Because that's the most important part. Are we going to go home and tell our friends and family how cool harmonics are? Awesome. I heard a yes. For the camera, I heard a yes. So sliders simulate pipes of different intervals of notes being played. So let's talk about playlists. Has anyone seen High Fidelity, the movie? All right, so in that movie, John Cusack talks a lot about the rules of making a playlist. And he's talking about the emotional rules, like what songs need to go in. But he also talks about the fact that you shouldn't elevate and then like deconstruct too quickly. And so all of those are effectively rules. And I love rules. I'm a programmer, and I work a lot with constraint solvers. And so I asked myself, like, can I take some of these rules, some of these music theory things, and build a solver with that? And I'll explain what a solver is. Don't worry if you're confused by that. That's totally natural. I was confused at first too until I saw the light. So what matters musically to a playlist? This is my theory. I don't know if this is like an official, like if you go to Wikipedia and you ask what matters to a playlist, I don't know if they would necessarily agree. But I would say tone matters to a playlist. So the chromatic compatibility that we were looking at before, like being in the same key or a complementary key or a fifth up or a fifth down. We'll explain what those are. The timing, which is spelled with the N in the second to last letter. So timing would be like the tempo and also the cadence, so whether you're in 3/4 or 4/4, or whether you're playing really fast in a tempo or really slow in a tempo with a lot of different notes. And the timbre represents like a lot about the instrumentation of the song as well. So let's talk about tone, because tone I think is the most interesting, and that's actually the rule that we're going to be focused on today during the talk. Before we do that, let's talk about modes. So raise your hand when I was asking before major, minor, who is not familiar with major, minor? Okay, that is enough of the audience that we're going to watch this video. So this is Jacob Collier. Is anyone familiar with Jacob Collier? He's a Grammy Award-winning musician. He signed to Quincy Jones's label. He was like a child prodigy at 15 and put a bunch of videos on YouTube where he was like harmonizing with people's random melodies. And so he did this series for Wired where he explained harmony to 5 different degrees of complexity. So first he explained it to a kindergartner, then he explained it to a grade school person, then he explained it to, I think, like a high school student, and eventually it was like Herbie Hancock. So he was like jamming out with Herbie Hancock, and that was really cool. But the way he explained it to a kindergartner I thought was really, really interesting, and he talks about major and minor.
Harmony is about injecting melody with emotion, so that ultimately you leave home and you return home and you've learned something along the way.
Yeah.
So a nice place to start is with the idea of a triad. A triad is a 3-part harmony, basically. So that's a triad, you know. So this triad is called C major. Right, so have you ever heard of this idea of like major chords and minor chords?
Yeah.
So this is C major, yeah? And then this is C minor. So the feelings are different, right?
Yeah, it feels like dark and spooky.
Yeah,
like
this one's dark and spooky. And how does this one make you feel then?
happy.
Right.
And joyful.
Yeah, I like that. Yeah.
Yeah, so it's an oversimplification. Again, very controversial subject in music theory, but effectively they have different, like you can't necessarily take a C major and go into a C minor and call that a musical transition when you're going from song to song. At least I don't believe that's the case. So there's this thing called the Camelot System. This is pretty canonical within the like turntables at a dance club DJ world, where basically you figure out what key a song is in. So let's say that we start with E major, and from E major I can play another song in E major. That's easy. That's like child's play. But I can also go down a fifth to A major. That's also acceptable because they share a lot of the same notes. I could go up a fifth to B major. They also share a lot of notes. Or I could go to a complementary key. So the complementary key, we were talking before about D flat minor and B flat major. Those are complementary keys. In this case, it's E major and D flat minor. And so has anyone heard of the circle of fifths? Okay, so the circle of fifths is basically just walking this Camelot scale clockwise or counterclockwise, ad infinitum. Like there's a lot of, like guitarists could do this all day and it would sound very musical and great. But you could also apply this to DJ sets, again, turntables in a nightclub. And one of the things that I discovered once I started getting out of turntables into the nightclub mode is you could also apply this to just regular playlists where you're playing one song after another and there's no real transition. That was one of the things that I did. That said, that's not me. That's someone that makes way more money than I do as a software engineer. But I did do mixtapes like post-college, and this was an example of one transition where I used the Camelot scale to figure out appropriate transitions between non-dance songs. So it was actually kind of hard to hear, but there was a little bit of a drone that was happening that was continued on from the previous song and the sustained note from the guitar. But the challenge is no one owns their media anymore. So like you can't really take these songs and like put them like together in like an audio sort of nonlinear editor. Like all music is basically in the cloud. Like it would be weird if I just gave someone a link to an S3 bucket and said, like, here, download my mixtape. I don't even know if people would know how to do that anymore. So, so almost everyone listens to their music in the cloud, which sort of posed a problem. It's good news for playlists because playlists are pervasive now. Even that Jacob Collier guy that we were looking at before, he put up a playlist that he adds to on a weekly basis of songs that he likes, and there's like thousands or millions of playlists on Spotify at this point. But people are even writing PhD theses about it, which is awesome. This is actually a really interesting paper on how like playlists have impacted our culture. But you can't do fancy tricks in Spotify, like play more than one song at a time. So what can we do? Well, we can reorder the tracks. It's revolutionary. We could take tracks A, B, and C and make it C, A, D, or make it D, A, whatever. I didn't list D in the first one, but that's all right. So anyone know Ryoichi Sakamoto? All right, finally, I found a reference that no one understood. All right, perfect. So Ryoichi Sakamoto is a Japanese composer, and he likes eating at fancy restaurants in Japan. But there was one restaurant that he ate at that he really, really hated the music. And for years, he secretly, he went to the owner of the restaurant and was like, hey, I'm going to program your playlist for me. I'm a really good musician. Don't tell anyone. I'm just going to, I'm going to make your playlist. And he applied all this music theory to the playlist. And then someone from the New York Times discovered it, and they wrote a whole article about it. It was really fascinating. He rejects the notion that algorithmic playlists are good, and I disagree with him. And he's probably right, because he's smarter than I am, but I'm still going to do this talk anyway. I thought about rewriting my whole talk, by the way, this morning to use quantum computing, because, but apparently we don't have enough qubits for that. So this is a talk about discrete optimization. Does anyone care to take a stab at defining discrete optimization? Good, because I've rehearsed an explanation. This is the Wikipedia page for the discrete optimization problem. It's too long. You didn't read it. Did anyone actually read the whole thing? No? Good. All right. So discrete just means that it has a finite number of possible solutions. So if I have a 10-track playlist, there are only a finite number of configurations of those tracks versus like an infinite number or continuous optimization, which could be like floating point integers ad infinitum at like infinite levels of precision. And optimization is searching those options to find one that closely matches a set of rules. So basically what you're looking to do is you're looking to minimize something or maximize something. In this case, it's minimizing the number of really ugly key changes in a playlist. So what are our rules? So songs should play exactly once. And some song transitions to be to songs in the same key. But unless we have a playlist of all songs in the same key, we're going to need other songs to transition to adjacent keys on the Camelot scale. So clockwise 1, counterclockwise 1, down or up 1. And song transitions should avoid drastic tempo or timbre changes as well. That's one of the nice things about discrete optimization tools like the one that we're using is you could just layer on all sorts of rules. You could say like, I don't want, I'm trying to think of a rapper or something. I don't want Beyonce to play after Chemical Brothers for some reason, or I don't want Jay-Z and Beyonce to play after each other because that's just like passé at this point. All the songs are in the cloud, so that's hard. How are we going to actually analyze the songs to figure out what key they're in? So this is a talk about API integration. Spotify has an amazing API, even though it's RESTful and not GraphQL. We'll fix that later. But they have an amazing API, which actually allows me to go grab all the playlists in JSON form with all the tracks, with all the artists, with all the album metadata. This is what it looks like to get a Spotify playlist. This is a JSON payload that's coming from them that uses OAuth. You sort of authenticate as the user that you're requesting on behalf of. So that's great and all, but what about the key? Does anyone know who this is? So that's Francis Scott Key. He wrote Star Spangled Banner, but that's aside the point. He's going to be our ambassador for a couple of times when we're asking about keys. The Spotify mergers and acquisitions team to the rescue. So Spotify acquired a company in 2014 that was doing some really, really cool stuff. They were a spinoff of the MIT Media Lab. And one of the things that they were doing is they were analyzing songs for all sorts of things, but one of the things they were analyzing for was key. and both the root note and the mode. And they're doing simple modes. They're not doing like Mixolydian and all that fancy stuff, but that's enough for me to work with. And so they actually introduced all the Echo Nest features into the Spotify API. So it turns out that in addition to all the track data, on 20 tracks per request, I can also get all this cool stuff. So what is this cool stuff? So they give me the key index. So that what they refer to as the key is really the fundamental frequency of the scale, or that's the root note of the scale. So in this case, the key is 2, which would be D, and the mode, which is 1 represents major, 0 represents minor. So I have that information now. I actually wrote software like a decade ago, over months, that tried to do something similar to this, and I was like, I fell out my chair when I realized that this was just available to me without having to write really any code other than a REST call. So they also bring some other helpful stuff for optimization. So they're returning their sort of analyzed tempo, the time signature, the loudness, but then they also have all these other properties like danceability, energy, speechiness, liveness. Speechiness is like how much is it like a podcast, I guess. It took me a while to understand. I thought they were referring to like, is it rap music or not? But no, it's like, is there musical stuff happening in the background? Is really then it's not considered speechy. These all down here are all intervals from 0 to 1. Okay, so we have the data now. Let's just assume we have the data. But how do we optimize? Anyone work with Optive Planner? You all should be working with Optive Planner. Is really, really cool software. So Optive Planner is a constraint solver for the JVM. It's open source, originally from the JBoss team, Red Hat, and now I think it's a part of IBM. I'm not actually sure what IBM's doing with it. But it's a Java library that you can embed, and we've embedded this often at Spantree to solve a lot of optimization problems. So some examples of non-Spotify optimization problems include trying to figure out if we're at a conference like this and you want to meet people that match your interests. Like one of the challenges when you have a conference of like 800 attendees is when and where to meet them. And if you have a conference that's all focused on meeting people, then all of a sudden like you're going to be sending emails back and forth. Hey, can you meet at 10? Oh no, this other person needs to meet at 10. I'm not going to be able to do that time. And so we wrote software that basically allowed everyone to say, like, I just want to meet with these 40 people. And then we say, great, give us your calendar, we'll figure it out. We've also written software for the state of Massachusetts to schedule foster care reviews for 12,000 children that need foster care reviews every month. Before that, there was, I think, 12 people that spent 3 weeks out of every 4 manually coming up with a schedule that we were able to hopefully reduce to the press of a button. So this is really cool software, and not a lot of people know about it, and we're going to go through some of it today. So first, if we're going to build a constraint solver in Optive Planner, we have to model our domain. So this is Kotlin. I'm using Kotlin, not because I hate Java, but just because I like Kotlin better. I'm sorry. So we model a track, and a track's going to basically mirror what we had in JSON format from the Spotify API. I took some liberties with the structure because there's a lot of things I don't care about for optimization. So the track is immutable. The track will always remain. It will always have the same album and artist and name, and it'll either remain explicit or not. But the playlist track, that could mutate. And the difference between a playlist track and a regular track, and just the track itself, is that the playlist track, some of the playlist tracks will have relationships to other tracks as far as like whether they go before or after. And we'll get into that in a second. So we're using a specific type of planning heuristic called chaining. So effectively, a playlist is a linked list, right? So I can model it such that I have a starting track, and then I have the next track, and that next track is going to point to the starting track, and then the next track is going to point to that track. And that actually turns out to be the most optimal approach when you need exactly one representation of all your planning entities. So I model out my first track, and that's effectively immutable. And then I modeled out what I'm calling my REST playlist track. I hate this name. Couldn't think of a better one by the time of the talk. But this is basically every track that's not the first track. And the difference is the REST playlist has a previous track value, which links to the playlist track. So that's effectively like a reverse linked list thing that we have going there. Is everyone kind of following that part? Okay, I see some nods. Good. So this is what that looks like. So effectively you have an anchor and then you have a chain of entities that point at other entities. And in certain planning situations, you can actually have multiple, like you can have trees of entities. In our particular case, it's all just linear because we're not playing like, this isn't a quantum playlist. That would be dope. But no, like there's no case where you're playing both like Beyonce and Jay-Z at the same time in different multiverses. So the first track remains fixed as an anchor. The rest playlist tracks have this planning variable of previous tracks. And then during optimization, what we're doing is we are basically just shuffling around the previous track value. So that's effectively how we're playing this game of playlist optimization, is we're saying instead of this playlist track going from one song to this song, I'm instead going to go from here to there. And then we determine whether or not that makes the score better or worse. So now let's build a planning solution. So this is a lot of code, and I'm using DexSet, and I learned this cool new feature called code highlighting that allows me to highlight just a small part of the code. So we're going to go through this like piece by piece. So we provide what's called a value range provider, and that will provide two lists in this case. So our anchor track, which is a viable previous track value, and then all of our rest tracks are also viable previous track values. And so we'll annotate our planning entity with the names of those ranges, and then that's what the Optive Planner system decides to use when it randomizes what moves it's making. We also have a series of facts. So these are other immutable things that sort of come along for the ride. And then we have a planning score. And the score is the star of the show because the score basically tries to keep track of how good this playlist is. And so this score is going to be directed by a series of rules that we're going to get into in a second. But effectively what we're trying to do, so in this particular score, there's 3 slots. There's one hard slot. That hard slot indicates that like this score is like this is a bad playlist altogether. So I'm playing the same song twice, right? Or I'm not playing the song that I really want to play. So that's an inviable solution. And then there's soft things, which are sort of nice to have, which is like in a perfect world, if left unchecked, I would never want to change keys. Now that's not reality. If you have a 100-song playlist, and unless you were like intentionally creating a playlist in one keys, you're going to have to change keys, but you want to try to keep that soft score as low as possible. So we have 2 of those. What the first slot represents the thing that we're going to be looking at today, which is just minimizing the key changes. And then the next one has more to do with the decay function of like, don't switch up keys on a regular basis. So if you just switched up keys, don't switch up keys again. So 0 hard, no feasibility issues with the solution. Soft, some things are still suboptimal at various degrees of severity, but we can accept that because we live in an imperfect world. So now let's write some rules. So Optive Planner has a sister project, or actually more technically, Optive Planner is a cousin or a nephew of Drools. It used to be called Drools Planner. Has anyone worked with Drools? Okay, all right. Eli, I didn't know you worked with Drools. Awesome. Eli's a Spantree. We're going to talk about that later. Drools is a rules engine, and I'm not going to get into a lot of detail on that, but I do have a lightning talk that I gave at the Chicago Java user group on Drools engines where we get into the algorithms and stuff, so I'll link that somewhere on like the website or something when I launch a website. But this is the rule for making sure that we play a song only once. So let's start with our when clause. So what we're doing is we're pattern matching. So we're saying when we have a rest playlist track and the previous track has been assigned, we're going to bind the previous track, this p variable, to the previous track. Now if we have another rest playlist track, and it'll automatically check to make sure that this isn't a duplicate, then if that other playlist track is also linking to the same previous track, then that's bad, right? That means we're playing the same song twice. We don't want to do that. So what we do in the then clause is we add what's called a hard constraint match, and we're going to penalize each instance of this pattern occurring in my solution by -1. Now, the -1 is important because what that means is that a perfect score is 0, and so you're always trying to get to the maximal score. If you have an unbounded solution set, then you can use a positive number, but in most cases, like, I've never actually come across a use case where that makes sense. And Jeffrey Desmet, the Optive Planner project lead, agrees with me. So just don't do it. Don't do it, Kevin. So this is the data structure that Jules uses. It's called the Reedy Tree, and effectively it compiles it down into this big tree where it can reason through changes in working memory very quickly. But what about key rules? Remember that guy, Francis Scott Key? He's keeping us honest. So for that, we're going to use what's called a shadow variable. And a shadow variable is something that listens to a change and runs some code to make some manipulations. So in this particular case, we have a shadow variable called key distance. And anytime the previous track changes, we're going to call, thank you, we're going to call the key distance function, or we're going to call this method to update the key distance function. So if, let's say, we went from an E major to an A major, the distance will be different on the Camelot scale. So that's what this code looks like. I'm not going to force you to look at all of it. So we have two events, after the entity is added or after the variable changed. And then this is the fancy math for us to figure out basically the distance on the Camelot scale. Because the distance could be closer clockwise or counterclockwise, we have to do this modulo function. I don't like writing this much code, but that's what had to happen in this particular case. And this is the part where we tell, oh my God. Okay, this is the part where we tell Optive Planner we've changed something new. Brew install ASCII Cinema to GIF. So I was trying to install this library that converted like terminal things to GIF, and I totally pasted it into the wrong part of my code. So, but let's pay attention to the playlist track key distance. Playlist track key distance. So anytime we detect that the new distance is different from the old distance, we're going to have to tell our score director that something updated before we update it, and then we're going to have to tell it when we're done updating it, because Java doesn't have a way to detect changes like that without like really, really bad performance. So now that we've done all this heavy lifting in Kotlin town, our key rule is very simple. All we have to do is say where we have a rest playlist track and the key distance is defined and the key distance is greater than 0, then take the key distance, so bind it, and then make the penalty, and in this case I'm doing basically the square of the key distance because I'm saying a distance of 2 is 4 times as worse than a distance of 1. So since most playlists contain more songs in more than one key, the score will never be 0. We can't always have nice things. But Optive Planner will try to find the most efficient path to minimizing unpleasant and drastic key changes. So this is a vehicle routing solver that the Optive Planner lead, Jeffrey, came up with. And what he's trying to do is trying to figure out where to send a bunch of trucks if I have a bunch of deliveries to optimize for fuel usage. Same algorithm. We're using the exact same stuff that he is, except we're doing it for Spotify instead of like reducing our carbon footprint. So how does it do that? So for that, we're going to go to chess for a second. So there's this problem in chess called n-queens, which is moving 4 queens on a chessboard such that they can attack each other. And so this is a move. What we're doing is we're saying instead of this queen being here, the queen's going to move to here. So it's going to change its position. And what Optive Planner is doing is it's trying to figure out all the possible moves that it can make given the current state. So certain moves will be impossible later on in the progression. So for example, if the board looks like this, all of a sudden there's moves that were once viable that are no longer viable, and so Optive Planner is going to ignore those. And Optive Planner just happens to be really good at making moves really quickly. Like this particular solver is doing about 3,000 move evaluations per second. Or this particular solver is doing like hundreds of thousands. My solver is doing about 3,000 per second. And it's also really efficient at figuring out which moves make sense. So it creates like automatically a bunch of move strategies that make sense. So some could be like you're swapping the previous track value. Some could be that you're just changing one. Some you're moving multiple. So how does this apply to playlists? This is what a solver looks like in action. It moves really fast and then it moves really slow. So the first thing it's doing is, we'll actually zoom in on these logs. What the hell was that? So the first thing we're doing is we're actually going to just try to pick some track to go as the previous track. So in this particular case, we're not undoing any moves. So that's what's called a construction heuristic. So what we're seeing is we're playing Kaki King after St. Vincent. And then that has some impact on the score. And then since we can't reconsider moves, once we've decided on a track transition, we're sort of stuck with it for a while, which makes it really fast, but makes it really inefficient because we'll quickly hit what's called a local optimum. So what if the Kaki King track was the only track that worked after Unknown Mortal Orchestra, but we've already thank you. We've already put Kaki King into play. Well, that's not going to work very well. So what we do next is what's called a local search. So the local search, it will effectively evaluate more moves and have the ability to undo. So it's going to be looking at, in this case, about 29 moves, evaluating which one is effectively the best with some sort of like probabilistic fuzzing. If it gets too far down a path, it can actually start backing up. And replaying some moves. So that's really fancy stuff that produces some really great stuff. So after a long while, we end up with an optimized solution. So in this case, like the score, I was running this on like a tiny, tiny VM. So after 600 seconds, we were able to find, I think this is like an 800 track playlist because I was trying to be really, really masochistic. But this was what came out. So this is actually, even though the scores are really, really low, low being negative, in this particular case, it actually was fairly good given the volume of tracks that we had. So most tracks will never get to a perfect solution, but Optive Planner is also really great in that it can tell us what's suboptimal. So after it gives us a result, it can actually tell you which transitions were the worst offenders of the specific rules. And so like this is some code that I wrote to basically output the fact that like this transition for whatever reason had to happen and they weren't able to undo it, or they weren't able to find an alternative, but it goes from a 1B on the Camelot scale all the way up to a 9A, which is a really far distance. But we only have one of those things out of 800 songs, so that's probably okay. So let's see it in action. This is a talk about failure. So I had planned to launch Spotfire IO by the time of this talk, so that you could all go there and you could paste in your Spotify playlist, and it would basically optimize and give you a new playlist under your Spotify ID. Due to Wi-Fi issues and procrastination and client fires and that sort of thing, I wasn't able to get it done, but I can talk about the different component parts. So the first thing we're going to do is we're going to pull data on demand from Spotify. I'm using this node library for that. We're going to slap some GraphQL on top. So we're using Apollo. Has anyone worked with Apollo? It's a node library for doing GraphQL. It's amazing. It's amazing stuff. I know you are. It's amazing stuff. We're also using this library called Prisma, which is the only ORM that I actually can tolerate. What it does is it will actually you define your GraphQL types, and it will create a database schema for you. And then all you do is you interact with the GraphQL interface, and under the covers, it's actually going to persist things. And so we're doing that basically to be kind to Spotify. If I just requested that artist, I'm not going to request it again. And then we can grab a playlist. So I actually built a GraphQL interface on top of Spotify's API using this caching layer. This is a strategy that we plan to do on other projects as well at Spantree. And now, once we've gathered all this playlist information, we can call this optimized mutation in GraphQL. And what it's going to do is it's going to gather all the data from Spotify and its cached objects, and it's going to output a tarball. And it's going to then post, this is the part that doesn't actually work yet, it's going to call an AWS Lambda with the address of that tarball. The Lambda is going to pick up that tarball, and it's going to do some optimization stuff, and it's going to phone home with the response, and then we're going to populate a playlist. So that's the piece I had working when Spotfire was a simple command line tool, and I decided to make it web and didn't finish. But what's up with this extract path? So this is a simplified form, but the extract path is basically just a SHA-256 hash, or at least the file name is a SHA-256 hash of the tarball contents. And it basically just contains a bunch of JSON line files with all the data that matters to the planner. So that's the part. This is the part that's not hooked up yet. Sorry, the font is super tiny, but I have a Lambda that I can invoke where I give it a JSON payload, and then that will run the Spotfire optimizer in AWS Lambda, and it will spit out a result. So it spits out a result and does nothing with it yet, but the goal is, again, to have it phone home. So it's coming soon. That was supposed to be an image of the Spotfire IO GitHub account. So I forgot to mention all this is open source. We're actually going to be using this as a reference architecture for planning projects at Spantree. And so if you actually go to GitHub, a lot of the code is crap, a lot of the code is commented out, but the website itself, along with the API, so the GraphQL shim, and the solver are all there. and I'll be continuing to update and doing some CI. And hopefully by next GOTO, you can come up to me, or if you actually tweet at Spantree, a Spotify URL, we'll go ahead and optimize it for you using these rules. So that's it. So I want to thank a few people, though, before I leave. So firstly, I want to thank Spantree and the Spantree team, especially Madi, Eli. Madi and Eli, because they built this really cool grid view for playlist tracks that I wasn't able to integrate. Eventually, I want to actually turn this into a full-on like playlist builder that's better than Spotify's own interface. And Justin for basically rubber ducking with me when I couldn't figure out how Optive Planner was working. I also want to thank the GOTO conference. I love this conference. It's one of my favorites. The Spotify and EchoNest teams for just being so awesome. And the Optive Planner, Apollo, Prisma, Postgres, it's like this whole chain is open source. And so I want to thank them as well. And I want to thank you for being such an exceptional audience. And if we do have questions, I do want to be respectful of the next speaker. We have a lounge at Spantree that many of you might have stopped by. It's over like on the way to the keynote lounge. We'll be taking questions there. So thank you.